Number 12.
That was difficult.
Did you get the correct graph? There was a minimum at, what was it? Negative 3 over 2 over 2? Comma negative 9 halves. And there was a maximum at 3 over 2 over 2 and positive 9 halves. There was a domain restriction because of the square root. It could only go between negative 3 and 3.
That was my problem.
So even though they had this whole like, do you see how they made one huge table for everything? What's going on here? Oh, it's an undefined negative 3. Oh, sorry. It's a 0. What's going on here? It's a critical number. There's another critical number too. What's going on here? It's a pip. They made one grand old Mama Bahama table to say, hey, critical numbers and pips and increasing, decreasing, and concavity. Let's do it all. Could you have done that? Yeah. But could you have also just put some pieces together, like had your first derivative sign chart with, what were your critical numbers?
3.
3 over root 2. Lovely.
Well, the critical numbers. The restriction is saying 3.
Oh, got it. Which means I should have ended this here, because if I tried to test something like negative 10, it would have been imaginary, or positive 10, it would have been imaginary. Some of you might have realized that, and some of you might not have. And then you would have gotten your, what? It's decreasing and then increasing and then decreasing. Do you see it? But then you would have also had to take your second derivative sign chart if you're doing them separately, like we're kind of used to. And you would have had your concave up and your concave down when you did all of your analysis. Did you guys have some intercepts you were supposed to find? What else? Symmetry. Did you guys get any? Awkward.
Odd.
Plug it in.
Odd.
Same, but the whole thing was opposite. So odd. See it? Origin symmetry. Any vertical asymptotes, horizontal asymptotes, oblique asymptotes?
No.
None. Domain, we already got negative 3 to 3. That was all the pre-cal stuff. And then calculus, we already got our critical numbers and our increasing, decreasing. Oops, sorry. Decreasing, increasing, decreasing. We have our pips and we have our concavities, and our point of inflection does exist at 0, 0. We have a relative min and a relative max. 14 IDs led to a graph. And you guys didn't even have to find derivatives unless you chose to do so. Anybody like choosing the hard way? Number 38. Did you realize there was a slanty asymptote? Did you realize there was a slanty asymptote? Why? Because the top's degree was bigger than the bottom by 1. So the slant asymptote, how did they get y equals x? Because if you did a long division, that guy divided by that guy, y equals x with a remainder, but we ignore that part for slanty asymptotes. Y equals x was that slanted line. And a relative max at and a relative min at. Oh, those are nasty decimals. If they're nasty decimals, what does that mean?
Calculator.
Which is why this said use a computer algebra system, right? Because would you have been able to find 1.6085 by hand? No.
Yeah.
No, Adam is plugging in numbers and he's going to find that thing is going to happen, right?
That is.
Now, he might have plugged in 1 and realized that 1 ends up with a negative number, and plugged in 2 and realized 2 ends up with a positive number, and so maybe he would have thought a little IDT action that it had to happen in between 1 and 2, but anyways. Pause. If you were allowed to use a calculator on number 38, couldn't you have found this with the calculator, just graphing it?
Yeah.
And this with the calculator, just graphing it? Can you grab out that special colored pen that is only for like AP stuff, or at least it jumps out of the page for you? How would you have highlight this one? Because you are allowed to be using your calculator. How would you have found this on your calculator? Is there an option for point of inflection in that really snazzy second trace menu? There's options for zeros, intercepts, for relative maxes, relative mins. At least intercepts that are hard, the x-intercepts, y-intercepts that you usually just plug in 0 to anything. But is there a point of inflection option? What do you guys think?
No.
Well,
Perhaps.
Nope. But we're allowed to use our calculator. calculator. We can do a min, we can do a max, we can do zeros, we could do that, right? We could plug in 0 for that, no big deal. Slanty asymptote, okay, you kind of got to figure that one out, but maybe you would see it seems to be getting closer and closer to a line. Maybe you could figure that one out. But long story short, the AP never asks for an oblique or slant asymptote. Well,
Shoot.
but it does ask for this. And sometimes you have calculator problems. Strategically, how small, what's the smallest amount of work that you would have to do if using your calculator to find a point of inflection? And I've already told you, graphing that and looking at it doesn't work.
Testing the signs.
Well, you define 2 derivatives then,
Yeah.
even though you have your calculator?
Couldn't you graph
You could graph the second derivative, and if we did graph the second derivative, do you guys see how it's concave up and then down and then up again? The second derivative, concave up until some sort of random point of inflection. Concave up means the second derivative has what type of sign?
Positive.
Positive, and if it's positive, if y values are positive, does that mean that the values are going to be above or below? Above. So it's going to somehow be like this. And then it goes concave. Does it start being concave down here, or does it start a little bit earlier? Earlier, right? Look at that curvature. So somewhere here, concave down means that f double prime is going to be negative or somehow below. And when does it change again? And that's not exactly f double prime because it probably has some weird like levelings off and stuff. But do you guys see how I have 2 pips? One here-ish and one here-ish, which are awkwardly in between the maxes and mins because their points of inflection, they're between the curvatures changing, not between like the highs and the lows, or not at the highs and lows. So, is Adam right? Could we graph the second derivative? Yes, but what would you be looking for?
Like where it crosses.
Can we do zeros on a calculator?
Yeah.
Yeah, we can. We can do like, hey, go there, find a 0, go there, find a 0. And any of these that have above to below or below to above will have a sign change of the second derivative, which means a concavity. Yes, we could have done that. Or we could have used our calculator that way without using a sign chart. But we would have to do calculus and find how many derivatives? 2. So I didn't ask just for what's a way to use your calculator to find it, which is totally fine. If I were you with your colored pen, points of inflection, how to use your calculator, you could graph f double prime and then find the zeros where f double prime changes from above to below or vice versa. Well, vice versa is going to take just about as long as to say just below to above. Long story short, f double prime zeros where there's a change. But I asked for what's the smallest amount of work that we would have to do. What would be easier than finding the second derivative? Finding the first derivative? And not having to go to the second derivative? What would happen at the graph of the first derivative with something like this?
Increasing, decreasing.
What are the zeros of a first derivative graph? How do I figure out where those are? These guys, I had to look for concavity change. How do I find zeros for f prime?
Relative extrema.
Relative extrema. So is there a 0 about here-ish? Right? And a 0 about here-ish? Somewhere, I kind of blew it out a little bit. At my maxes and mins now, true? What are all the slopes coming in towards the relative max? What signs do they have?
Negative.
Positive, because what is my function doing? Increasing, right? So positive, well wait, if my function is increasing and my f prime is positive, so before this relative max, is it above or below? It meaning the first derivative. Above or below if my function is increasing? Above. Okay, and then what does it start doing? My function starts decreasing, which means f prime has to go below, but just a little bit, because it goes down a little bit and then it comes back up. Wait, why am I back at a 0? Because what have I hit? My horizontal tangent. And then what does my function start doing again?
Increase.
Okay. No, hold on. Wait, so they look the exact same? Well...
That's creepy.
Don't like that.
What were the signs of my second derivative? If my second derivative at this awkward, I don't know, A, and at this awkward, I don't know, B. If my second derivative is a positive, then a negative, then a positive, yes, we know that f is concave up, concave down, and then concave up. But my question is, what is f prime doing? Increasing. Whoa. Decreasing. And then increasing. Increasing, decreasing, and increasing? I'm wrong. It doesn't decrease down to that. It actually goes steeper up until that A guy. It's going to go somehow steeper until it then starts decreasing. And then it's going to decrease until it increases. Do you guys know where f prime's relative maximum is? Where f prime changes from increasing to decreasing?
There.
A. Wait, what was so special about A? Who is A? The point of inflection! And then guess where this one's going to be?
B.
Where f prime changes from decreasing to increasing. B. And what's B? The point of inflection. So guess what? The other way of doing it is to only have to find one derivative and then locate the relative maximums and minimums. How do you find points of inflection? Either with the first derivative or with the second derivative. If it's an easy second derivative, find the zeros. It's fast. If it's a hard second derivative, stop at the first derivative and just find the maximums and minimums. Because look, won't the maximums and minimums of f prime be the points of inflection?
Yep.
That's a really cool calculus trick that the AP forces you to do at least a couple times. All right. Sorry, we've been having too much fun with AP stuff when I'm supposed to be talking about optimization today. Number 66, you guys can check it out. Wait a minute, did I give you guys very many evens last night?
No.
Nope, and that was on purpose. Is 66 our last one?
I think 80.
Oh, do we have one more? Oh, 80. You have increasing on these two intervals, -4 to 2 and -2 to 1. F prime is increasing, aka f is concave up on -2 to 0. You have a relative max at 1 and no relative min. Then you have points of inflection at -2 and 0. And some of the things we just talked about would have been helpful. But I'm guessing, isn't 66 a multiple choice? No, it's not. It's given a graph of a derivative.
89, 91, and multiple choice.
Got it. Number 80. Number 80 is a how do you see it? Guys, are number 66 and 80 kind of involved?
Yes.
Yes. Do you think there's a lot of AP concepts I could start talking about right now?
Yeah.
Yes. So we're going to table questions on those latter, deeper, conceptual-ish questions, if you guys don't mind, and save those for the beginning of class tomorrow. Sound good? They're really good, they're really important, but for getting the general idea of section 3.5, it wasn't actually the point, it was just exposure to AP type analysis, if that makes sense. That was our last one, okay. Test review, what? Oh, remember, this used to be the last section of chapter 3A. Okay, we need to go ahead and get back to optimization. Homework questions on this tomorrow. So if you guys need any extra time with the answer key, you know it's going to be online. Oh, that didn't work. But we need to get back to this guy. So as you guys are putting away your homework spirals and as you are getting out your notes, those kiddos that are just joining us, I don't think you've seen this page yet. We were talking about it for a bit at the beginning of class as I was trying to get life all settled and figured out after being stuck in traffic for quite a while. Been one of those years. And the class was totally well supervised and all of that. Mm-hmm. Oh dear. So we were talking about at the beginning of class optimization and whether or not anybody had ever heard of it before. Optimization, we talked about how optimistic sounds like maybe it came from it, and maybe optimal. Optimistic, you guys give me a quick summary. If you're optimistic, what does that mean?
Thinking of the brighter side of when.
Brighter side of life, or the best possible way of looking at life in some ways.
Outcome.
Best possible outcome, also good. Optimal solution, best possible solution. Then we went to business and said, hey, maxes and mins, is that something to do with the best possible? And yes, it's everything. It's fine. To do with the best possible. One of these days I'll get coffee. Minimums. Let's minimize costs. Maximums. Let's maximize profits. Okay, but let's figure out what on earth is going on so that you guys have some sort of clue when it comes to homework. Now guys, here's the long story short. There is a yellow box, and the yellow box is going to be helpful, and I am going to come back here every now and then just to give you some terminology, just to give you some vocabulary as to what we're doing, kind of like related rates, but I do not need you to make this a forever card. Because at the very end of the day, if I was to unfreeze the screen, at the very end of the day, these are max-min problems that says use calculus to find maxes and mins. And yeah, we've been there and we've done that, just not with word problems. So
What? What'd you say?
Interesting.
Oh.
we have one simple one and we have one more involved one. Let's see how the simple one works. We're just finding maxes and mins. We're just finding maxes and mins. Don't worry, we're just back to notes. You got it. You haven't missed too much. Here we go. Maxes and mins. Question. Where in the wording does this example problem give you the idea of find the max or find the min? The A and B. Because this says as
Small as possible.
AKA find the
Min.
min, and this one as
Large.
okay, so you're going to literally be seeing the words min and max. Maybe not, but you're going to have wordings that point you in that direction. Find a number. Aw, there are no variables. But what did we do? You just did test corrections. What are you supposed to do in word problems if there are no variables given?
Make them.
Make them. Find a
Baseball
number.
problem.
Sure, let's call them x. Oh, that's right. And a closed interval. Hey, we have endpoints. Such that the sum, come on, you math students, sum means
Addition.
of the number, what is his name?
X.
And it meaning the numbers.
Reciprocal.
1 over.
Reciprocal.
X.
1 over.
Okay, so it means
Now, hold on. Whenever we're dealing with a derivative, we want to take a derivative of a function or of an equation. We don't have an equals right now, right?
yeah.
So we name it whatever the heck we want to name it. Now if it's one of these problems over here, we might have to name it like A for area, or V for volume, or P for perimeter, or C for cost. Anyway, but have they given us any ideas to what we should call them?
X problem.
But we already used X. Let's not use
Name it
X.
Joe.
Want to name it Joe? So
No.
J of X.
Yeah. Wait, but who?
Because it's our job to find. I don't know. J of X.
No, you.
Why did I make it an equation? Because we're used to taking derivatives of equations, so it's going to be a lot easier.
Ugh.
Wait, derivatives, why are we taking because to find maximums and minimums
Well,
of a
use
continuous, this is not continuous domain problem. Remember, think of your constraints. We're constrained by x can't be z, it doesn't matter.
In there.
It doesn't
Well, we
matter.
have to still put the domain.
Well,
It's helpful.
yeah. John, if this was in between, we would have to do like a sign chart analysis instead of a simple table plugin. But the nice thing is, the function is, Wyatt, thank you, EDT, continuous on a closed interval. He doesn't make any issues here. Well, sweet. All we have to do to find maximums and minimums is make a table and say who's biggest and who's, wait, don't we
Who's
need
biggest?
critical numbers and endpoints? Why have I left space? Because what have we not done yet?
Crits.
And how do we find crits? Derive.
Drinking derive.
Now, don't we really want like a nice fraction so the top equal to 0 and the bottom equal to 0? So maybe would you want to get a common denominator and then derive using the quotient rule to get a nice fraction?
No.
Maybe. But if you don't like that idea, you can always take the derivative piece by piece. I just took a derivative seeing this guy as x to the negative 1 and using a power rule. But long story short, we should probably eventually get a common denominator so that we can get that nice little fraction, because we don't want to start moving stuff around and not factoring, because we'll start losing answers. Anyway, now that we have a derivative, top equal to 0, that's at negative 1 and 1, but why am I crossing out negative 1?
Because it's not in the interval.
So 1's the only other guy to consider. And whenever I am testing critical numbers and endpoints, where am I plugging into to figure out how high it goes and how low it goes?
Derivative. I mean original.
Why?
Sorry, my brain.
Derivative will just tell me how fast it's increasing or decreasing, not
The
where it
value.
is. So if I plug in 1/2, 1/2 plus 2 is 2.5, 2.5, I'm just being lazy. If I plug in 1, 1 plus 1 is 2, that's kind of low. Plug in 3/2, 3/2 plus 2/3, number plus its reciprocal. Aw, 3/2 plus 2/3, I might have to actually do some math.
It's like 2.
Wouldn't that be 9/6 plus 4/6, which would be 13/6? Which is 2 1/6?
Which is not bigger than 2.
So where's my absolute max? Right here. And where's my absolute min? Right here.
Wow.
Because the lowest it goes is 2 and the highest it goes is 2.5. Now hold on. You are answering a question. What are they actually asking for? Find
A number.
Then who do they want?
The
I don't know.
X value.
1/2.
Oh.
1/2 plus its reciprocal is going to be the highest. Oh wait, wrong one. 1/2 plus its reciprocal is going to be the highest. And 1 plus his reciprocal is going to be the lowest.
Wow.
Dun, 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 dun. You have to be careful of those words and know what you're looking for. Could given and find be a good idea?
Oh.
Yeah. Cute piano though. Okay.
Have you had coffee?
How about example number 2?
I don't think she did.
So I want you to be able to start homework. Wait, guys, is all of homework just like, hey, it's a max or min, try to make equations and take a derivative and
Oh,
then
yeah.
handle?
No, ma'am. Word problem.
Hold on. Let's get a word problem. A rectangular plot of land. We always know to draw a picture. I know it's step 1 in your notes, but don't we always draw a picture if we need to?
Yeah.
Cool. 2 different kinds of fencing. What? 2 opposite sides will be heavy-duty fencing. Well, I guess I'll call the heavy-duty guy X. For $3 a foot, I think that's important. And then the other 2 sides will use standard fencing. I guess we'll call that Y. Selling for $2 a foot. Where do we want the heavy-duty? I don't know, pretend there's a river in the water, I don't know, we'll just call that X. And then the standard fencing, I'm not sure, not as much to protect from, I guess, we'll call that Y. What are the dimensions? What are we trying to find? How big the plot of land is? X by Y feet. You guys have heard of a 2x4, right? A 2x4 is giving you the dimensions of the piece of wood. So dimensions, it's going to be width times length or length times width or whatever. It's going to be a something by something field. Why is this a max or min problem? What are the dimensions?
You could have a lot of the expensive. Or a lot of the.
What are they telling us? You only have how much money? What are my constraints? You only have $6,000. So your cost is going to be between 0 to 6,000. Now my guess is if you're trying to, wait, what kind of field are we trying to get?
Rectangle.
Do you see it? But yeah, the biggest area in a rectangle that's possible with these
You need one
constraints.
more underline, damn it.
Okay, so we're trying to do the greatest area for the max area. So wait, what are we supposed to be finding eventually? A prime. Well, wait a minute. How do we don't even have an equation for area. Area, it's a rectangle. What's area formulas for rectangles?
Squared.
Someone.
Hey,
Make
dog.
circles.
Nice.
Oh,
baby. But we're gonna need that in a second. Area is x times y.
You had a pie in there.
Oh, yes.
But hold on.
Where would you say? That's a 2.
Here's the problem though, guys.
That's a circle.
I want a prime of x and I have a y in there. He doesn't belong, and this is not an implicit problem. Guess what? There's this extra clue. If we're labeling things, this would be called our primary goal, and this would be our secondary. Why am I writing this in blue? Because we're going to call him our... It's going to be our blues clue. It's going to be our hint that we have to go to our handy-dandy notebook and say, oh, that was important. Because if we have $3 for both of those, and if we have $2 for both of those, and if that needs to equal $6,000, can I maybe get an expression for y?
Why?
Yes.
That I could plug in and then take a derivative? We're going to have to be playing with our information to get to. You guys can get ready to get out. Max or min, take a derivative of something, but we only want one variable. No implicit in this section. Bye, guys. I'll see you later. Homework starts with something like example 1, then it gets to example number 2.
So we can start homework with example 1, continue until we get to example 2.
Well, we started example 2.
Unless we come into
I think I might record period 6 today. We'll see. You guys got cut short on time.